Have you ever wondered how the moon was formed? How did our planet get such a beautiful and faithful companion in the sky? Well, the most widely accepted theory is that the moon was created by a giant collision between Earth and another planet-sized object about 4.5 billion years ago. This object is called Theia, and it was roughly the size of Mars. The impact was so powerful that it blasted a huge amount of material into orbit, which eventually coalesced into the moon. But what happened to Theia? Did it completely vaporize or merge with Earth? Or did it leave behind some traces of its existence on our planet? In this video, we will explore a new theory that suggests that the collision that formed the moon could also be the cause of mysterious blobs hidden in Earth's core. These blobs are called Large Low-Velocity Provinces, or LLVPs, and they are two massive structures deep within the Earth's mantle, one beneath Africa and the other beneath the Pacific Ocean. The theory proposes that these blobs are remnants of Theia that sank into the Earth's mantle and solidified into the LLVPs. We will also see how this theory was tested by computer simulations and what it means for our understanding of the moon's origin and the Earth's evolution. So, if you are curious about the moon's secret origin and how a collision left behind blobs in Earth's core, stay tuned and watch this video till the end. Before we dive into the new theory, let's first understand what the LLVPs are and why they are mysterious. The LLVPs are two huge regions in the lowermost part of the Earth's mantle, the layer of hot and molten rock that surrounds the core. The LLVPs are about 1,000 kilometers thick and cover about 10% of the Earth's surface area. They are called low-velocity provinces because seismic waves, the vibrations that travel through the Earth after an earthquake, slow down when they pass through them. This indicates that the LLVPs have different physical or chemical properties than the rest of the mantle. But what are these properties, and how did they come to be? That's the big question that scientists have been trying to answer for decades. There are several theories that try to explain the origin and nature of the LLVPs, but none of them are fully satisfactory. Some of these theories are oceanic crust accumulation. This theory suggests that the LLVPs are made of old and dense oceanic crust that sank into the mantle over billions of years. The oceanic crust is the outer layer of the Earth that forms the ocean floor, and it is constantly recycled by the process of plate tectonics, where the crust moves and collides with other plates. When the oceanic crust subducts or slides under another plate, it can sink deeper into the mantle and accumulate at the bottom. However, this theory has some problems, such as the amount and composition of the oceanic crust needed to form the LLVPs and the lack of evidence for such a large-scale subduction in the past. Another theory is chemical differentiation. This theory suggests that the LLVPs are made of primordial material that was separated from the rest of the mantle during the early stages of the Earth's formation. The primordial material is the original material that the Earth was made of before it differentiated into layers of different density and composition. The theory proposes that the primordial material was denser and richer in iron than the rest of the mantle, and that it sank to the bottom and formed the LLVPs. However, this theory also has some problems, such as the timing and mechanism of the separation and the thermal and chemical stability of the primordial material over billions of years. As you can see, the LLVPs are still a mystery, and none of the existing theories can fully explain their origin and nature. But what if there is another possibility, one that involves the moon and a cosmic collision? Now, let's move on to the new theory that proposes that the collision that formed the moon could also create the LLVPs. This theory is based on the idea that the impact between Earth and Theia was not a head-on collision, but a glancing blow, where Theia hit Earth at an angle. This means that some of Theia's material did not vaporize or merge with Earth, but remained intact and continued to orbit around Earth. Some of this material eventually joined the moon, while some of it fell back to Earth and penetrated the mantle. The theory suggests that the material that fell back to Earth was denser and more metallic than the mantle, and that it sank to the bottom and formed the LLVPs. It also suggests that the material that joined the moon was lighter and more silicate-rich than the mantle, and that it formed the moon's crust and mantle. This explains why the moon has a different composition and density than the Earth, and why the LLVPs have a different composition and density than the rest of the mantle. The theory also explains why the LLVPs are located beneath Africa and the Pacific Ocean, because these are the regions where the material from Theia would have landed, according to the angle and direction of the impact. It also explains why the LLVPs have a blob-like shape, because the material from Theia would have deformed and stretched as it sank through the mantle. So, how does this theory compare to the other theories we discussed before? Well, unlike the oceanic crust accumulation theory, this theory does not require a large amount of oceanic crust to form the LLVPs, and it does not depend on the history of plate tectonics. Unlike the chemical differentiation theory, this theory does not require a primordial material to separate from the mantle, and it does not have to deal with the thermal and chemical stability issues. In fact, this theory can account for the observed features of the LLVPs, such as their density, composition, and thermal state, better than the other theories. But how can we test this theory? How can we prove that the LLVPs are indeed remnants of Theia? This is where computer simulations come in. To test the new theory, a team of researchers from Arizona State University and the University of Chicago used computer simulations to model the collision between Earth and Theia and track the fate of Theia's material in the Earth's mantle. They used a powerful supercomputer called Mira, which can perform 10 quadrillion calculations per second, to run hundreds of simulations with different initial conditions and parameters, such as the size, speed, angle, and composition of Theia. They also used the latest data and constraints from geophysics, geochemistry, and planetary science to make their simulations as realistic as possible. The results of their simulations were published in the journal Nature, and they support the new theory that the LLVPs are remnants of Theia. The simulations showed that the collision between Earth and Theia could indeed produce a moon with a different composition and density than the Earth, and that some of Theia's material could fall back to Earth and sink into the mantle. They also showed that the material that fell back to Earth could match the observed location and shape of the LLVPs, depending on the angle and direction of the impact. Moreover, they showed that the material that fell back to Earth could have different physical and chemical properties than the rest of the mantle, such as lower seismic velocity, higher density, higher iron content, and higher temperature. These properties are consistent with the measurements and estimates of the LLVPs from seismic and geodynamic studies. They also showed that the material that fell back to Earth could remain stable and isolated in the lowermost mantle for billions of years, without mixing with or dissolving with the surrounding mantle. Therefore, these simulations provide strong evidence for the new theory that the LLVPs are remnants of Theia, and that the collision that formed the moon could also create the blobs in Earth's core. However, the simulations are not perfect, and they have some limitations and uncertainties. For example, they do not include the effects of mantle convection, the process that transfers heat and material within the mantle, which could affect the distribution and evolution of the LLVPs. They also do not include the effects of the core-mantle boundary or the interface between the core and the mantle, which could affect the interaction and stability of the LLVPs. The simulations also have a limited resolution, and they cannot capture the fine details and variations of the LLVPs. They also have a range of possible outcomes, and they cannot pinpoint the exact scenario that happened in reality. Therefore, the simulations are not conclusive, and they need to be validated and refined with more data and experiments. We hope you enjoyed this video and learned something new and interesting. If you did, please give us a like, share, and subscribe to our channel for more videos like this. And don't forget to leave us a comment below. Thank you for watching, and see you next time.